end of finite automata chapter. So this is a finite automata. The language being accepted by a finite automata is known as regular language. Regular language. Okay. Now, given a set of language, this one. If somebody asks to identify the language which are not regular, or I'll say which are not regular language. How to identify that one means, say for example, given a language, if you could design a DFA or an NFA or a regular expression for that particular language, then we can conclude that this language is regular language. But how to check that this is not a regular language means we need to check whether any DFA exists for that one, whether any NFA exists for that one, whether any regular expression could be constructed for the given language. So this is an infinite number of ways to be done. So it is very hard to identify whether a given language is not regular or not. Okay. Now today we are going to learn one theorem which is known as pumping lemma for regular language. Okay. Later on we'll be explaining why the term pumping has been added with this particular lemma. Okay, the name, it's a pumping lemma for regular language. Why pumping has been included? Once we understand this one, right, we'll be knowing it later. Now, this particular lemma, right, is used to identify whether a given language is not a regular. Given the language is not a regular. Okay. Now, the main concept being used for this particular is known as pigeonhole principle. Okay, why I'm explaining principle means the concept which is going to be utilized by this pumping lemma for regular language is pigeonhole principle. So let me explain this pigeonhole principle. Consider there are three pigeonholes. There are three pigeonholes. There are three pigeonholes, and then there are four pigeons. There are four pigeons. Okay, there are four pigeons. There are four pigeons. Then if suppose I'm going to place each pigeon inside this particular pigeonhole, each pigeon inside this particular pigeonhole, then let me number this pigeon as 1, 2, 3, 4. And then let me designate some symbol or something for this pigeonholes. Let me say it A, B, C. These pigeons also, they are finite in number, but greater than the number of pigeonholes. Again, this pigeonhole also finite in number, which is lesser than number of pigeonhole. Number of pigeon. Now, if I want to place each pigeon inside this particular pigeonhole one by one, if suppose I'm going to start placing this first pigeon inside this A, and then second one inside this, and then the third one will be here, fourth one remains. Fourth one, right, I have to place inside the pigeonhole. So it means what? Out of this three pigeonhole, there will be one pigeonhole which will be consisting of more than one pigeon. Got the point? There are three pigeonholes, and then we have four pigeons. If suppose you're going to place all these pigeons one by one inside this pigeonhole, then what we are going to do is, what will happen is, one of the pigeonhole will be having more than one number of pigeons. That is the concept of pigeonhole principle. And then how we are going to utilize this one for this pumping lemma for regular languages. If suppose we are going to design a DFA, we are going to design a DFA for a language which ends with a string 01. Let me just design a DFA which ends with string 01. Q naught, Q1, Q2, 01. If it starts with 1 and then ends with 01, it will be accepted. Again, if it starts with 0, series of 0, and then after that it ends with 1, then it will be accepted. 1, 1, 1, 1, 0, 1 will be accepted. 1, 0, 0, 0, 0, 0, 0, 1 will be accepted. 0, 0, 0, 0, 1 will be accepted. And then after this 1, if it is 0, then after 1, if it is 0, and then followed by 1 will be accepted. So 1, then 0. So 0, 1. And then what about 1? If it is going to be 1, then this is a DFA. Now, when I say that given the language, I'm going to design a DFA for a language, it's a combination of 0, comma 1, and then ends with this one, where W belongs to 0, comma 1, string closer. So it means what? The language is infinite in nature, but the DFA, the number of states in the DFA is finite in nature. Okay, so the string length might vary, might increase, might be more than number of states. Here, the number of states is m is equal to 3. But the string length, right? String length, the first one which I have tried to take, right? It is how much? How many? I mean, 1, 2, 3, 4, 5, 6. 6 in number. What about this one? 1, 2, 3, 4, 5, 6, 7. 7. What about this one? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 7. The value of the string length, right? It's 677. But the number of DFA is fixed. M is equal to 3. I have designed a DFA to accept a language which consists of 0 and 1 and ends with 0, 1 here. Okay. Now say for example, consider this Q0, Q1, Q2 as the pigeonhole. Consider this A, B, C, like this is Q0, Q1, Q2 as the prison. If you're going to Q0, 1, you're not supposed to repeat any state. I'm going to check for 0, 0, 0, 1. Let me check this one. We're going to check for 0, 1, Q1, then 1, Q2. Now let me check for this 0, 0, 0, 1. It will start from Q0 and then 0, Q1. Then self loop, so Q1, Q1, Q1. After this, Q2. Now see here, I have considered that, I have explained to you that I'm trying to relate how this pigeonhole principle is related with this DFA and all. Okay, that's relation I'm explaining right now. See here, the string which we are considering right here as number of pigeon here, and then the states for this particular DFA, right, they are being considered as the pigeonhole. So if the number of length keeps on increasing, right, definitely one of the state needs to be repeated. One of the states needs to be repeated. So in our example, Q1 is walked by this particular pigeon for 1, 2, 3, 4 times. Okay, that is the concept which we are going to utilize pigeonhole principle for proving relate be repeated. How many times it's going to be repeated depends on the string. And then in our example, 1 second. Now, so this is the relation I just want to show about this one. Now, regarding this pumping lemma, right, let me start explaining. Take a language L, take a language L. In my case, let me consider what to say. Okay, 0 to the power n. Okay, where n is greater than or equal to 1. This is, let me take one series of zeros. So pumping lemma, I'm going to explain, okay? Out of this language, take a string of it. Okay, take a string of it. Language is nothing but a collection of string. In this case, this will be 0, 0, 0, 0, 0, 0, then 0, 0, 0, 0, then 0, 0, 0, 0, 0, then like that. Okay, this is a collection of string. Out of this collection, right, I'm going to take one string that will be represented by W. It's up to me whether you're going to take this, 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 or this. It's up to you. Now let me consider this. Okay, one part of this language I'm going to consider. That one part, let me consider as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let me consider 0 to the power 11th as a portion from this particular language. Now, as per this pumping lemma, right, they're asking us to split this W into 3 portions. So let me rewrite this 0 for 11 part. 11 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so I'm explaining pumping lemma. Okay, I've started explaining it. This W of length, 0 of length 11, I have written it here. Once again, okay, so this one, right, as per pumping lemma, you have to split it into 3 parts. This W has to be split into 3 parts, X, Y, Z. And then whether how many of zeros you want to consider as X, Y, Z, it's up to you. It's up to you. But one condition is there. One condition is there that Y should not be empty. The condition is Y another X. Let me consider this as X. Let me consider this as Y. Let me consider this as Z. So as per pumping lemma, right? Given the language L, from that particular L, consider a string W from that L. Definitely W is a subset of L, hence the length will be definitely lesser than L's length. So W, or if you want, instead of 0 to the power 11, we can consider 0 to the power m also, where m is less than n, like that. Okay, because this is n, 11th I have considered for simple explanation purpose. So don't get confused. Later on, I'll be using only this alphabetical small letter alphabet for representing the length and all. But for the time being, I'm not using such things. Definitely 11 is less than n. Okay, so now the meaning, now after this, right, after splitting this W into 3 substring X, Y, Z, the only condition is you cannot select like this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What they meant by this is X, Z, Y is equal to null, like that. You cannot select like this as per pumping lemma. Y should be at least a single symbol or character, or a substring of length 1, at least 1. Okay. So after splitting this into 3 parts, right, increase the length of this string W in this portion. Okay. Now X to the power I Z, where I is greater than or equal to 0. Okay. Now W is equal to 0 to the power 11th. Now we are going to increase the length of W by some value. Okay, like maybe 11 plus I, we are going to increase. But where we are going to increase means you should not increase in the substring X part or Z part. You have to increase in the substring portion of Y. And then this is Y to the power I. As per the pumping lemma, right, they're asking us to pump the value of this I infinitely. Okay, to pump the pump in the value of I infinitely. Now, as per pumping lemma, right, I'm going to increase the length of Y because I'm trying to increase the length of W by some values. That some values where to be added means in here. Now let me increase it 0, 0, 0. This is X. Now let me choose I is equal to 2. Let me choose I is equal to 2. So I is equal to 2, then this is y, right? Y to the power y to the power I is equal to y to the power 2. So y you need to write twice. So I've written this for twice. Rest 1, 2, 1, 2, 3, 4, 5, 6. This is 6. 1, 2, 3, 4, 5, 6. Okay. Now after increasing the length at y, now let me count the number of string here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This is 13. Whether after increasing the length of w by 2, whether this still belongs to L, we need to check. Now as per the given language for us, L is nothing but 0 to the power m. Now this is 0, then twice 0, then like this, keeps on increasing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, like that, okay? So hence, after increasing the length of W by some values at Y portion, 0 to the power 13 still belongs to L. Then L is a regular language. Got it? This is the explanation. Now let me take another one. This is for language. This is for L as a regular language. I've considered one simple example. Okay, I haven't written any statement officially. Let me explain another one. Now see here. Let me take another example. L is equal to 0 to the power n, 1 to the power n, where n is greater than or equal to 1. Now again, same thing, I'll do it. L is nothing but 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, 1, because number of by number of ones, the number as for this language provided. Now again, same thing, I'll do it. Consider one string from this language. Let me consider W is equal to 0, 0, 0, 1, 1, 1. And then as per pumping lemma, let me write as per pumping lemma for regular language, I have to split this into 3 parts. So W is equal to 0, 0, 0, 1, 1, 1. 3 parts, it's up to me which part you just want to consider as what to say, Y. It's up to me. First one, let me just consider this as X. Let me consider this as Y. Let me consider this as Z. Okay. Now again, after splitting this W into 3 parts, right, we are going to pump the value of Y I times. Now we need to check we need to check X I to the power I, where I greater than or equal to 0 is still belongs to L. We need to check. Okay. Now let me check I. Let me take I values equal to 2. Now this, not this. Now let me write W is equal to 0, 0, 0 to the power I, 1, 1, 1. Okay, and then I value I have considered as 2. So let me write 1, 2, 1, 2, 1, 2, 3. Okay. Now after this, right, this is equivalent to 0, 1, 2, 3, 4, 5, 1, 3. Whether this still belongs to L? No. Why? Because the language provided to us, right? The language provided to us is if 0 is 5, the number of 0 is 5, 1 should be of same value. But after pumping in, after increasing the length of W by I times, right? This does not belong to the given language L. So hence L is not a regular language. L is not a regular language. Okay, this is the explanation for pumping lemma for regular language. Now let me come to the formal statement of this one. Okay. I'm not writing the whole this things. Okay. I'm just writing this part because I don't want to provide the full definition of it. From my side, please try to have a look from the textbook also. That's why I'm writing this part alone. Okay. What do in textbook and all you can find this xy less than or equal to small p like that. That's nothing but pumping length. And I just want to explain one more thing here. Even though I is greater than or equal to 0, but why am I always checking equal to 2? Why am I checking for I is equal to 0? Now, what's the purpose of this power I? What is the purpose of this y to the power I? It's nothing but it will help us to increase the length of W. Okay, depending on the value of I, it will help us to increase the length of this W. Now, when I take I is equal to 0, when I consider I is equal to 0, then the pumping lemma, they have provided a condition that the length of Y should be greater than or equal to 1. Okay, the length of Y should be greater than or equal to 1. Hence, that I value is equivalent to 0 violates the second condition, which is already given in the pumping lemma for regular language itself. That's why we are not taking I is equal to 0 value because of this reason. And then what about I is equal to 1? I is equal to 1 value, even though it is feasible, because when I is equal to 1, it means what? Y is not empty. But still, why are you not considering this one? Now, the purpose itself will explain this one to us. Our purpose is to increase the length of W. If the y is equal to 1, y to the power I, then I is equal to 1, then the length will be same as it is. We are not increasing it actually. When the from what value of I itself, the value will start increasing means from the value of I is equal to 2. That's why even though by default for simplicity reasons they have just given that I value should be a positive value, but you might get confused sometimes. Why can't we take I is equal to 0 values? Why can't we take I is equal to 1 values? Okay, that is the reason. And then now for simple explanation purpose, I have considered what language here 0 to the power n, 1 to the power n, and then have considered a little bit, like value related things calculation we have done, and then we have proved that this language is not a regular language. So it's the same language, let me consider it, but instead of considering of this value like 11 or 5 or 6 like that, I'll be considering a general value. Let me consider one example. You might be confusing why this W, this and all. Purposely, I'm doing this so that you please go back and read the pumping lemma for regular language from the textbook at once. So let me take another example, a general example, and then let me finish this class. Now, let me take one example. L is equal to 0 to the power n, 1 to the power n greater than or equal to 0. Proves that this is not regular. Okay. Now solution. Let me consider a string. W is equal to 0 to the power m, 1 to the power m, where m is less than n. It means what? The length of this one is twice n. Okay, the length of this language is twice n, but I have considered a value m, a string, a subpart of this language L. M is less than n. It means what? W is a part of this language. Don't get confused. If you are confused, go back to that previous example and then just check by yourself. Okay. Now, W, right? We need to split it up into what to say? Three parts. Three parts, right? Now, how am I going to split it? Means in textbook they'll be showing three cases. Three cases mean 0, 0, 0, 1, 1. First case they'll show x, y in this part itself, and then rest z. Second case, y is a combination of 0, 1. Third case, y is in this part. No need for showing all those cases. Okay. It's good. It's good to show like that. It's good. It means briefly you are understanding the concept. Okay. But now in this example, I won't be showing like that. Okay. Now I have a string of power m, 1 to the power m. Now from the pumping lemma for regular language, let me write it shortcut in this manner. From this, x, y to the power I, z needs to belongs to L, where I is greater than or equal to 0. Right. Now let me take y is equal to 0 to the power k, where 1, I mean k is greater than or equal to 1, but less than or equal to m. Got the point? X, Y, Z, right? This X, Y, Z, this is 0, 0, 0, 0, 0, 1, 1, 1, 1, 1. I have considered this as Y, and number of 0 is K. Hence, K value is less than M. Even K is greater than 1 because we need not keep Y value as empty. So K value is, lesser than M, greater than 1. Okay. Now I have selected y as this, and then if you want, you can precisely say x is equal to 0 to the power p, then z is equal to 1 to the power m. Okay, I'm splitting this like this. Z, x, number of zeros in x portion is p, number of zeros in y is k, number of ones in z is m. But the length of this should be p plus k plus m should be equal to twice m as per this string length. Okay. Now let me select I is equal to 2. Now let me select I is equal to 2. Then If you get confused in this portion, you just go back and check the previous examples. Okay, I is equal to 2, then 0 to the power p, 0 to the power k plus 2, then 1m. Now this length is greater than twice m. Hence, got the point. I mean, instead of saying greater than twice m, let me do it in a very precise manner. Let me do it in a very precise manner. Now this will be 0 to the power p, 0 to the power k plus 2, then 1 like this. As we know, p plus k plus 2, p plus k plus 2 should be equivalent to m. But because number of zeros should be equivalent to number of 1, p plus k plus 2 should be equal to, instead of writing equal to here, let me just write must be equal to, what to say, number of 1. But p plus k plus 2 is greater than m, which means W does not belong to L. Hence, L is not regular language. Okay, so my advice to you guys is, I'm applying this pumping lemma as a general cases, and then I have proof that the given language, this one is not regular in this way. And then if you are confused with this one, right, please refer this one, because it's almost the same. But for simplicity reasons, I have considered a finite values here. But in exam, you should not prove the given language as the given language is not regular, not in this manner. You should be in a general, precise manner, like what we have done by these values and all. I have explained what are the. Now, what you need to do language by yourself in a written any statement related to I just, and then so you please statement is very important. There are 1 mark like that, like pumping him up for regular length like that. Okay, so this is the end of. Wait one to call someone randomly. Unmute your mic and you should respond to me. Safety Katiyar. Absent. Then Waripam Mangalsana.
Present, ma'am.
Absent. Okay,
Present.
present. Vishal Jaiswal. Waripam Mangalsana absent. Vishal Jaiswal.
Ma'am, Warappa Mangasana
Vishal
present.
Jaiswal. Yeah, present. I have marked it. Vishal Jaiswal. Absent. Harish Kumar.
Yes, ma'am.
Okay. Deepak Kumar.